Hello everyone, I am Joybrata Chaudhary, a PhD student at the Robert Bosch Center for Cyber-Physical Systems, Indian Institute of Science, Bangalore. This talk is about our paper, Deep Attention-Driven Reinforcement Learning, DADRL, for Autonomous Vehicle Decision Making in Dynamic Environment, with my co-authors V. Shivaraman, Sumit Dangi, Professor Suresh Sundaram, and Professor P. B. Sujit. I am thankful to Qualcomm for supporting this work with the Qualcomm Innovation Fellowship. Imagine a unsignalized traffic condition. The ego vehicle in red has to take a left turn. In this condition, only a few of all the surrounding vehicles are important than others. Most current models often treat all surrounding vehicles equally, which is unrealistic. This simplification fails to capture the varying importance of different vehicles in influencing the AV's behavior. In real-world scenarios, only a few vehicles significantly impact the AV's decision-making. Identifying and prioritizing these key vehicles is crucial for ensuring safe and efficient navigation. However, the importance of each vehicle is not static. It changes constantly based on its actions and the evolving traffic scenario. Hence, a model must account for both spatial, that is position and distance, and temporal, like speed and acceleration factors to accurately assess vehicle importance. This novel approach allows the AV to continuously update the importance of each vehicle in real time. By focusing on the most critical vehicles, the AV can make safer and more efficient navigation decisions. By accurately assessing and prioritizing interactions, the AV can better anticipate and react to potential hazards. Focusing on key vehicles can optimize decision-making process and improve overall traffic flow. The model can adapt to dynamic and complex traffic situations, making it more robust in real-world scenarios. We have introduced the Deep Attention-Driven Reinforcement Learning or DADRL framework, which prioritizes interaction based on their importance. We have developed a self-attention mechanism incorporating a masking signal tailored to the ego vehicle's perspective. In conjunction with a context map, this enhanced attention mechanism feeds into the soft actor critic or SSC algorithm, which then determines the appropriate maneuvering actions. So spatiotemporal attention encoder gets the inputs which are historical kinematic states of ego and surrounding vehicles. A shared LSTM network is utilized to capture temporal dependencies in vehicle movements for past 2.1 seconds. Attention mechanism models actually ego attention. It considers ego as query and surrounding vehicles as both key and value. We focus on attention weights associated with the ego on other vehicles. The attention mechanism outputs spatiotemporal attention encoding of surrounding vehicles. Another part is context encoder. Here, inputs are bird's eye view context map including drivable area and waypoint maps. We employed a convolutional neural network to extract relevant features from the images. It outputs context encoding vectors. For final state encoding, we combine the spatiotemporal attention encoding from STAE and context encoding vector from the context encoder. This concatenated vector serves as the state space representation for RL-based decision making. We tested DADRL in different scenarios. One such scenario is left turn. This scenario is based on an urban setting where the ego vehicle has to maneuver through an unprotected left turn with heavy traffic at a T-junction. Navigating this scenario can be quite challenging due to several reasons. There are no dedicated traffic signals to control the turn. The ego vehicle must judge the right moment to make the turn based on the traffic flow on the continuing road. If the continuing road has heavy traffic, finding a safe gap to execute the turn becomes even more difficult. The ego vehicle must accurately assess the speed and distance of oncoming vehicles to ensure a safe turn. The structure of the intersection and parked or moving vehicles can limit the visibility. So ego vehicle has to see the oncoming traffic from the left and then take the decision. The ego vehicle must make a complex decision making taking into account all these factors, and any mistake can lead to accidents. Another scenario is roundabout. This urban roundabout driving scenario typically involves a circular intersection where traffic flows in one direction around a central island with multiple exits leading to different roads. The ego vehicle transitions from a two-lane bidirectional road to a two-lane unidirectional roundabout with four exits. We use three versions: roundabout A, B, and C, with increasing difficulties in that order. The ego vehicle is supposed to cover a quarter, half, and three quarters in roundabout A, B, and C respectively. So there are some challenges in this scenario. Traffic in a roundabout moves in a unidirectional circular pattern. This requires the ego vehicle to merge with the moving traffic at the right time and speed, which can be difficult, especially in heavy traffic conditions. In a multi-lane roundabout, lane discipline becomes crucial. The ego vehicle must stay in the correct lane based on its intended exit, and changing lanes within the roundabout can be complex due to the circular traffic flow. Another scenario is double merge. In this scenario, an AV starts from a single lane road, navigates to two-lane one-way road with two entrances or exits, and exits on the opposite side. The ego vehicle must effectively perform lane changes amidst this traffic flow from all entrances and exits, honing its navigation and lane changing skills. So challenges are: the ego vehicle must safely merge with other vehicles in the lane it is merging into. This requires accurately judging the speed and distance of other vehicles and finding a safe gap in the traffic. Traffic flow can be unpredictable in merge areas with vehicles slowing down, speeding up, or changing lanes. The ego vehicle must understand these movements and react accordingly. Our evaluation of the DADRL method was conducted using the SMARTS simulator. We benchmarked its performance against a spectrum of methodologies, including rule-based system, established deep reinforcement learning techniques, decision transformers, and an amalgamation of transformer encoder-decoder architectures with deep RL strategies. The findings were clear. DADRL surpasses former leading-edge methods, delivering superior results in terms of both success rate and collision metrics. Success rate represents the proportion of episodes where the agent successfully reaches the goal out of the total evaluation episodes. Collision rate is the proportion of the episodes that resulted in a collision between the agent and surrounding vehicles. A lower collision rate signifies better navigation and avoidance capabilities. We also conducted ablation studies for DADRL method with other metrics. Humanness error is calculated based on the comfort factors such as jerk and angular acceleration. It assesses how closely the agent's movements resemble human-like driving behavior. Overall score depicts a comprehensive measure of driving performance. As implemented in SMARTS, it combines multiple factors such as progress, rule violation, and comfort. Humanness error and overall score are both provided by SMART simulator. Distance to destination metric shows how close the proposed method finishes its path. The context-free method is for only using spatiotemporal attention encoder or STA and without using the context map. Also, SMC here shows if we do not use attention mechanism how the performance is. It is clear from the plots that the attention modeling is important. Also, we can see that using context maps are helpful. In summary, this work shows the challenges faced by the recent decision-making algorithms. It shows the importance of interaction modeling in a dynamic driving environment. It proposed a novel ego-vehicle oriented attention mechanism. Future work can model the interaction better by incorporating a dynamics model of the ego vehicle.